Section 6.3 and 6.4, the definite integral and the area. Let's suppose we have some function f of x. And so let's just take a graph in the plane. We're going to sketch some function f of x. And there's a restriction here, and that is f of x is a continuous non-negative function on the interval. And so that just means that if we have some a value and some b value, and so I'm going to put a here and b here, then if we have this function, it being non-negative just means it's above the x-axis, and the fact that it's continuous, for lack of too much detail, is if you start sketching the graph, when you put your pen down, you don't have to pick it back up, okay? And so let's say that we have some graph, some function, f of x. Then what happens is that if I want to find the area of the region shaded under the graph between a and b and bounded above the x-axis, well, what does that look like? Specifically, that's going to be the region under the graph between a and b. And so if you fill in all of this region in here, I claim that this is the area that we're referring to. The integral is actually going to answer the question for this. It's going to allow us to find the area under a curve bounded between a and b and the x-axis. And so let's start by something we should know how to do, and that's say that we want to find the area, this blue area of this shaded triangle. Okay, so recognize that this is a triangle between -2 and 0, and these are vertical lines, so this is a right angle. And then all I need to do is, if I want to remember what is the area of a triangle, well, the area of a triangle is 1/2 the base times the height. And so the base here is the distance between 0 and -2, but that's a distance of 2. And the height here is between 0 and 2, and that's also a distance of 2. And so if I want to find this area, that is 1/2 of 2 times 2, or 1/2 of 4, which is just 2. And so I claim that the area of this triangle should be 2 if everything is what we expect it to be. Now, back to that statement, area under a graph. If we have some function f of x that is continuous and non-negative on some specific interval from a to b, where a is less than or equal to x, which is less than or equal to b, then I claim that the area under that function can be found by taking the definite integral from a to b of the function f of x dx. And I claim that this is the area that we're referring to above, that shaded region under the graph. Okay, so now if we're claiming that the definite integral finds this area, recognizing that the area of a triangle is 1/2 the base times the height, I should be able to calculate this area using the integral for this function f of x being -x from -2 to 0. So let's try this. Alright, so our function, we're taking the integral from -2 to 0. Do make sure that you're going from least value to greatest value when you do these, otherwise you'll end up with the negative using the definite integral properties that we referred to previously. And so you do have to make sure they're in the correct smallest to largest value. We're taking the integral of f of x, which is -x dx. Okay, great. Well, then let's do this. Well, what's the antiderivative of -x? Well, that's going to be negative x to the second divided by 2. And then we need to evaluate it from -2 to 0. Okay, so then what do we get? This is going to be -0 squared over 2 minus -2 quantity squared over 2. And what do we get? Then we get 0 minus times minus is plus. -2 quantity squared is 4. 4 over 2 is equal to 2. So at least we should be led to believe that it's possible that these two are the same. And I claim that they absolutely are. If you have a non-negative function and you're trying to find the bounded region between the vertical lines a to b under the function but above the x-axis, the definite integral does give you that solution. And so now let's just extend this concept to several shapes. So let's say that we're giving this figure here, where specifically our function is negative x minus 1 times x minus 4. That is our curve. And then we want to figure out what is the shaded region here. What is the shaded region between the values 1 and 4? Okay, well, I do recall that we don't really have a product rule for integrals, so I'm going to go ahead and simplify this function. And so this is negative, and then I'm going to use binomial multiplication, FOIL if you so desire. X times x is x squared, minus 4x minus x plus 4. Then I'm going to distribute that negative sign, but I'm also going to simplify this. And so minus 4 minus 1 is negative 5. And so this is then going to be negative x squared plus 5x minus 4. That is the function that we're looking at here. And so I just went ahead and did that because we're going to need it to find the antiderivative. And so then, to find the area of this shaded region under the curve, bounded above the x-axis and between 1 and 4, that is the integral from 1 to 4 of negative x squared plus 5x minus 4 dx. And so first, let's find the antiderivative. So the antiderivative of negative x squared is negative x cubed over 3 plus antiderivative of 5x is 5x squared over 2 minus the antiderivative of 4 is 4x, and then we evaluate this from 1 to 4. So then we just plug our values in. This is negative 4 cubed divided by 3 plus 5 times 4 squared divided by 2 minus 4 times 4 minus, be careful with your brackets, negative 1 cubed over 3 plus 5 times 1 squared over 2 minus 4 times 1. And so I get this is negative 64 thirds plus 40 minus 16 plus 1/3 minus 5 halves plus 4, which I get to be 9 halves. And so I claim that the area of that shaded region is 9 halves. So for number 3, let's suppose that this graph that is drawn here is the graph 3x squared plus 4x plus 5 times e to the x over 5. We want to find the area of that shaded region. Recognize that the shaded region is bound between 0 and 2. So we're going to take the definite integral from 0 to 2 of 3x squared plus 4x plus 5 times e to the x over 5 dx. Step 1, of course, is to find the antiderivative. That's going to be 3x cubed over 3 plus 4x squared over 2 plus 5 times e to the x over 5 divided by 1/5. And then from our limits of integration, which are from 0 to 2. And I'm going to go ahead and do the simplification here, because 3 divided by 3 is going to give us 1, so this is x cubed plus 4 over 2 is 2x squared. And then 5 divided by 1/5 is multiplied by the reciprocal of the denominator, and so that's going to be plus 25e to the x over 5. And then we're evaluating it from 0 to 2. And so then this becomes 2 cubed plus 2 times 2 squared plus 25 times e to the 2/5 minus 0 cubed plus 2 times 0 squared plus 25 times e to the 0 over 5. And so let's notice that then we have 8 plus 8 plus 25 times e to the 2/5 minus 0, 0, and e to the 0 power is 1, and so minus 25. And so I get that this is exactly negative 9 plus 25 times e to the 2/5. And so that is our exact solution, but if someone asked us to approximate, we could of course approximate. And so if we want an approximate value, let's just round to 3 decimal places. This is 28.296 square units of whatever those units are. And so, once again, the exact solution and an approximation. Now let's extend this geometric idea, and let's say that we have 2 functions. Now, for the sake of our claim, we're going to assume that our function f of x is always above g of x. And so there's also some weird, interesting things that we can do. But let's say that I have this function, f of x, and I have some other function, g of x. Doesn't really matter what they look like too much. But if we suppose that there exists some a value and some b value, and we specifically want to find the area between a and b and between these functions, then I claim that that area is going to be equal to the integral from a to b of the top function, f of x, minus the bottom function, g of x, and so we can find the area between 2 graphs. Now, we do have to be a little bit careful, because if we suppose that in certain places there's a crossing and the graphs cross each other, you may have to use some of our properties of definite integrals to actually break them apart to do calculations. And so just keep in mind that when you're evaluating these definite integrals, this f, whatever you're putting before the subtraction, has to be above the one you're subtracting. Okay. Now, with all this being stated, that does mean that we're going to have to slightly graph every single one of these, at least enough to get the idea of what our functions look like. Okay? And so let's say that I want to find the area of the region enclosed by the curves y equal x cubed and y equals 2x squared. And we're going to have to figure out where they intersect. So let's graph y equals x cubed. Well, what does y equals x cubed look like? It looks about like this. Okay, so this is y equals x cubed. Then let's graph y equals 2x squared. Well, y equals 2x squared, that 2 being multiplied is going to make it taller and skinnier. And so there's actually a slight problem here. I don't know where my intersection points are, but I think this is going to be something like this. Okay. Now I do have to confirm this to figure out where these things actually intersect. And so let's figure out where they intersect. And so to figure out where they intersect, I just need to set the equations equal to each other. So that is x cubed is equal to 2x squared. And so solve, subtract 2x squared, subtract 2x squared. X cubed minus 2x squared is equal to 0. Factor out x squared, that is x squared times x minus 2 is equal to 0. Then zero product property, x squared is equal to 0, x minus 2 is equal to 0, and so we get that x is equal to 0, and x is equal to, add 2, x is equal to 2. And so specifically, I now know that my locations of intersection are at x being equal to 0 and at x being equal to 2. Now if I were to zoom into this graph, and so let's actually do this, let's zoom into this graph. If I zoom in, now at this point I do have the problem, and I don't actually know which one is above which is larger, x cubed or x squared. Now because I am aware at this point that I know the intersection points are at 0 and at 2, I know that that's where they cross, but how can I figure out which one's above and which one's below? Well, I'm going to pick a value between 0 and 2, and I'm going to plug it into both of these equations. So let's let x equal 1. Well, then if I let x equal 1 and I plug it into my equations, that's going to give me 1 cubed is equal to 1, and 2 times 1 squared is equal to 2. Recognize that at this point I'm actually seeing that 2 times x squared is bigger than x cubed, and so a little bit off, I'm going to correct it. It should actually look like this, and I know that my intersection point is there. Okay, great. So now with all this being the case, the shaded region that I'm actually trying to calculate is this little sliver between those two functions. Okay, well, let's figure out how big that area actually is. And so how do we find that area? Well, the area between those two curves is going to be the integral from 0 to 2 of the one that's higher up, which we now see as y is equal to 2x squared. So that's going to be 2x squared minus the function below, which is x cubed dx. And so now, looking at those intersections, finding that sliver, we just have to find the antiderivative. And so that's going to be the integral from 0 to 2. And so now the antiderivatives are, well, the antiderivative of 2x squared is going to be 2x cubed over 3 minus x to the 4th over 4 from 0 to 2. That's going to be 2 times 2 cubed over 3 minus 2 to the 4th over 4 minus all of that function with 0 plugged in, but that's just going to be 0 cubed is 0 times 2 is 0 divided by 3 is still 0 minus 0, so that's just minus 0. And so then we get 16 thirds minus 16 fourths, or 4, which I get to be 4 thirds. And so now I know that the area bounded between those two curves is 4 thirds. So now we want to find the area of this shaded region below, which is bounded on top and bottom by the two curves given. Now, the problem is that in this picture, nobody's told us which one is which, and so we actually need to figure out which one is which. Now, a few things. Recognize that it's bounded from here to here, and so I can see that A is -1 and B is 3. Then, figuring out which one's bigger, the quickest and easiest calculation I can think to do is to throw 0 in here. And so let's do that first one. 0 squared minus 50. Well, that's going to give us -50. And so if that's correct, then that should be that this bottom one is y is equal to x squared minus 50. But let's continue this confirmation. Then y is going to be equal to 0 times 0 minus 2 minus 25, but 0 times any number is 0. 0 minus 25 is minus 25, and this does line up. And so our top one is y is equal to x times x minus 2 minus 25, and our bottom one is x squared minus 50. And so with this being the case, if I want to find this shaded region here, I'm just going to find that the area is equal to the integral from -1 to 3 of the top, which is x times x minus 2 minus 25 minus x squared minus 50. And so then at this point, we can, well, don't forget our dx. I'm going to do some simplification of this first, and then find my antiderivative. And so this is then the integral from -1 to 3 of x squared minus 2x minus 25 minus x squared plus 50 dx. I see that I can simplify a few more things. X squared minus x squared is going to be 0. And so this is then the integral from -1 to 3, -1 to 3 of x squared minus x squared, well, that's 0, minus 2x minus 25 plus 50 is plus 25 dx. Well, then my antiderivative here, I get to be -2 x squared over 2 plus 25x from negative 1 to 3. And so this then gives me, I'm going to do one more simplification, that is, this is negative x squared plus 25x from negative 1 to 3, which is then negative 3 squared plus 25 times 3 minus negative 1 squared plus 25 times negative 1. And so I get this is negative 9 plus 75 plus 1 plus 25, just distributing that negative and being a little bit careful. And I get that this is equal to 92. And so now I know that the shaded region trapped between those two functions is a square unit area of 92.